All right, Physics 30s, Mr. T here. We're looking at Unit 6 on nuclear theory. Here's a little comic at the home for old atoms. There's a laugh and a half. Okay, anyways, nuclear physics is where we start, and atomic nuclei. Scattering experiments, 1911 to 1913. Rutherford and others showed that the nucleus was composed of protons, P positive, and neutrons, N. These quantized nuclear particles, we call them nucleons. Three parts to the atom. We've got electrons, protons, and neutrons. You can see the electrons' charge is -1, protons +1, and neutrons 0. The mass. Now, the mass is in atomic mass units, and an atomic mass unit is approximately 1.66 times 10 to the -27 kilograms. The mass of the electron, since it is very small compared to the proton and neutron, it's assigned a mass number of 0. Proton and neutron, 1 each. Okay, nuclear notation. To fully describe the nucleus of an atom like sodium-25, here's the notation we're going to be using. So Na is a symbol for sodium, 25 is the mass number, and 11 is the atomic number. You can see the mass number is the mass of the nucleus in atomic mass units, and it's the total number of nucleons, which is 25. The atomic number is the number of protons. That determines which element it is, and sodium is element number 11. And it's the charge of the nucleus in elementary charges, which means there's 11 protons there, each with a +1 charge. Isotopes have the same number of protons, same element, but different numbers of neutrons. They have the same chemical properties, thus they can form the same compounds. However, they can have different nuclear properties. Some are stable, while others are radioactive. Okay, we're going to talk about the nucleus without discussing the strong force. The protons of the nucleus are very close together. Since they have like charges, there is a strong repulsion force, a high electrostatic force, or electric force. The strong nuclear force has the following properties. It's force of attraction that acts between any pair of neutrons. In other words, neutron to nucleon, I should say. Neutron, 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 proton, and proton, proton. It is a short force, so it's over a short range. While the distances are very short, 10 to the -15 meters, it is the strongest force in nature. But when the distance increases, the force decreases dramatically. All right, stability. There are 400 isotopes that are stable, not radioactive. Small stable atoms, less than 20 protons, typically have equal numbers of protons and neutrons. But as the atom gets larger and larger, more protons, greater than 20, it'll have more neutrons than protons. Okay, mass energy equivalence, nuclear mass defect. The total mass of a stable nucleus is always less than the sum of the masses of its constituent protons and neutrons. The difference in mass is called the mass defect, delta M of the nucleus. To calculate the mass defect, you can use this formula here. Delta M is total mass of protons and neutrons. Subtract the actual nuclear mass. For mass energy equivalence, in 1905, Einstein proposed that mass was another form of energy. Thus, the mass that was lost in the nucleus when it was first constructed was converted to another form of energy. To calculate the equivalent energy from the mass defect, Einstein introduced his most famous formula. E equals delta mc squared. Well, delta m is the mass defect in kilograms, c is the speed of light in meters per second, and E is the energy converted from mass in joules. As a result of this, physicists introduced a more general conservation law, the law of conservation of mass energy. Note, subatomic masses are often expressed in terms of the electron volt unit, eV over c squared. To illustrate, consider the conversion of one atomic mass unit, MeV over c squared, over unit 2 MeV over c squared. First, convert to kilograms. So delta M is one atomic mass unit, so 1 U is 1.66 E negative 27 kilograms. Next, use Einstein's formula to convert this mass to energy. So E equals delta mc squared. So calculate this. You get 1.494 times 10 to the -10 joules, which is about 934 mega electron volts. Finally, convert it to the desired unit. In other words, M is E over c squared, so just put 934 MeV over c squared. All right, we'll do binding energy in just a moment.